Alright guys, this is section 7.2 and this is on properties of powers, also known as like exponent laws. So I think this will be a easy section, lots of algebra today, and one that you will enjoy. There's a journal selection for you in case that floats your fancy. I think that some of you will think that's easy and some of you aren't as good of coming up with ways to memorize rules. So it's there if you like it, write about it. Okay. The good news about this section is most of it is very, makes sense, obvious, whatever you want to say. What does x to the third times x to the fifth mean? Well, x to the third is x times x times x. Times x to the fifth, well that's times x times x times x times x times x. All of a sudden, I have x to the 1, 2, 3, 4, 5, 6, 7, 8. Okay? What did I do here? Well, I took the 3 and I added it to the 5 because that's how many times I multiplied. It was repeated multiplication. There was 3 here and then there was 5 more, so it's a total of 8. This is called the product of powers postulate. And it states that whenever you have the same base and you have different exponents, you can add the exponents and get a total. Okay? So how about this one? What does x to the 8th over x to the 4th mean? Well, that means x times x times x. I got quite a few of them here. 8 to be exact, right? So that's x to the 8th over x to the 4th. Well, let's talk about this. I have x over x. Well, that's just 1. So that kind of cancels. I kind of hate when people say cancel. It simplifies down to 1. X over x, there it happens again. Oh, here's another one. Oh, it happens a total of 4 times. So I'm left with just x to the 4th on top and 1 on bottom, but we can just leave it as x to the 4th. What's another way you can think of that? Well, 8 subtract 4, because all the duplicates cancel or simplify down to 1, and I'm left with x to the 4th. So this is the quotient of powers theorem, and it states when you have the same base, this only works when you have the same base, guys, and different exponents, you can subtract them. So you take the top minus what's on bottom. Okay, the power of a power. Okay, what does xy to the 5th mean? Well, we have xy times xy times xy times xy times xy. Now this can be written as x times y times x times y times x times y. This is just expanding it further. And if I wanted to, because multiplication is commutative, I can rearrange this so all the x's are first. How many are there? 1, 2, 3, 4, 5. And I can follow it up with the y's. And what do I have? X to the 5th, y to the 5th. This should make sense to you. Oh yeah, I see it. Okay, here's what the power of a product postulate states. If you have a product, a multiplication problem, and that whole multiplication problem is taken to a power, you can kind of, you could take each piece to that power. Okay, I call this is a word I totally made up. This is not a mathematical word at all. Pow tribute. It reminds you of distributing, but it's not distributing. So I call it pow tributing. You take the power inside here to everybody. So in this case, a to the m, b to the m. But if you really think about what this means to begin with, this rule should make perfect sense to you. Okay, now this one is a fun problem. How many zeros are at the end of this when written in base 10? And I don't want you to use your calculators to figure this out. I want you to think of it a different way. Okay, and hopefully you can see this, but what we're going to do is all about rearranging the numbers. 13 times, look, 5 times 2 times 5 times 2 times 5 times 2. Oh, there's 10, 10, 10. So 13 times 10 times 10 times 10. 13 times 10 to the 3rd. How many zeros are there going to be? There's going to be 3 zeros. I'm curious as to if you guys figured this out or not before I showed it to you, because the new math, this everyday math, and the UCSMP is really big on number sense, and that's rearranging numbers so that they make more sense. And this is something that I would never have been able to figure out very well whenever I was a student, because we looked very much left to right. But I think some of you guys probably saw that right away. The 5 and the 2 go together to make 10, so you can figure out the number of zeros. This is a power of a quotient theorem. What does x over y to the fourth mean? Well, just expand it, and we get this. If you remember how to multiply fractions, you multiply the top, you keep them on top, multiply the bottoms, keep them on bottom. And that gives me x to the fourth over y to the fourth. Same thing as before, really. If you have a quotient or a fraction and it is raised to some power, n, you can contribute again, but you need to take the top to that power and the bottom to that power. The parentheses are going to be a big sign that you will be doing some contributing, like I call it. Zero exponent theorem, this is one super important, and this will probably come up on ACT. I feel like they like to throw this in there just to see. And your calculator knows the answer to this. Anything to the 0 power is 1. So what is 2 to the 0? 1. What is x to the 0? Oh yeah, it's 1. What is 32 to the 0 power? Pretty sure that's 1. Smiley face to the 0 power? Yes, that too is 1. How come? This comes from the rule we discussed right back here, the quotient of powers theorem, where you subtract exponents. How can I get 0? I can get 0 if I subtracted the same number top and bottom. N minus n is 0, right? But we both know if everything canceled out, I'm not left with 0, because that's 1, that's 1, that's 1, and that's 1. I'm left with 1. I'm not left with 0, because you can't just make things go away if you started with something to begin with. Okay, power of a power. This one, what does this mean? X to the third squared. Well, that means x to the third times x to the third, and we know what that means. That means you can add those. So that is x to the 6th. Is there a shortcut here? Yes, there is. You could have multiplied the exponents. Power of a power states if you have a power and it's raised to some power, you can multiply the exponents to get a total. All right, write as a whole number or a simple fraction. We're going to do this work in your head, and that's kind of accurate and kind of not. And I don't know how blurry this is going to be. Okay, so let's do some of these together. Negative 4 squared, that's going to be positive 16. 233 to the first power, 233. 10 to any power is adding zeros or moving decimal points. This is a scientific notation review. 110 moves it to 89, and I'm going to add 4 zeros. 1 over 15 the first is just 1 over 15. I have no clue why that's there, so ignore that problem. Anything to the 0 power is 1. Here is a parenthesis and a exponent on the outside, so we will power tribute here. This is 3 to the third over 4 to the third. It's 27, I think, over 64. 511 times what? That's 1. It's 511. This one, I don't know why that's there either. What do I do here? Well, 10 to the 12, 10 to the 12. I'm going to cancel. 1.2 over 1.6, that is not a nice way to leave a fraction with a decimal in it, so I'm going to move both those over, and I get 12 over 16. That's also not a nice way, because that reduces. 4 is in common to both of them. That is 3/4. You will get better at this as time goes on. These rules should become second-hand nature the more and more you practice. Okay, these are really hard to see. Let me think what I can do here. What if I put... Are you impressed? I fixed it. Okay. Rewrite as a single power. I'm actually probably just going to do this odd column here, feel free to pause the video and work ahead, or mark down any that you couldn't figure out, and we could talk about them in class tomorrow. Here I have a base, and it's the power to a power, so that will be 4 to the 6. That is a single power, and that's how they want me to express my answer. Here I have the same base, 5 and 3, I can subtract. That is 8 squared. When they're spread out, I can add them. This will be 4 to the 6th power. 7 to the 12th over 0 is just 7 to the 12th. Power to a power, I'm going to multiply. That's 3 to the 1st power, which is just 3. Okay, here's power to a power, multiply, x to the 18th. I will add x to the 12th. This one I'm pretty confident you will get wrong if you do this on your own. When I tribute here, I have to take 3 to that power, and then I have power to a power. So that's 3 to the 4th, d to the 12th. Kids miss these all the time. Be very careful. Everything gets taken to that power. 3 to the 4th is, I believe, 81, d to the 12th. Be really careful there. Here, I have 5 times 2. Also, don't forget to take that. 10, m to the, I will add 8. Here, same thing. Negative 4 squared becomes positive 16. Be careful with signs here. And I have g squared. And this one is my favorite. This will be x to the 16th, because this one is done in parts. 2 to the 3rd, x to the 12th. 2 to the 3rd is 8, x to the 12th. This will all be multiplied. So that's going to be 8x to the 28th. Okay, I'm going to go ahead and do the evens too, because it's fun for me, and I think some of you could benefit from checking your work here. So hopefully you worked ahead to see if you get these right before I go through them. I'm going to add 2 to the 8th. I will subtract 3 minus 2, 12 to the 1st power, which is just 12. Like bases, they're spread out here. I will add them, 3 to the 7th. 10 to the 8th over 10 to the 5th. I'm thinking about canceling here. That is going to be 10 to the 3rd power. This one is a little more confusing. You have a couple options here. The rule says you should subtract, so if you get 10 to the negative 5, that is okay. Some of you who are thinking about this as the canceling might have 1 over 10 to the 5th. I will tell you those two are equivalent, but we will talk more about negative exponents, and I don't know if it's tomorrow or the next day. Okay, this is power to a power and power of a product. Everything gets multiplied here, so I have 4 to the 3rd, w to the 6th. 4 times 4 is 16. 16 times 4, I believe, is 64, I think. Tell me if I'm wrong tomorrow. It's r to the 15th. Here, don't forget to multiply the 7 and the 8. That's 56. Y to the 8th. 7 times 2 is 14. Add the exponents. Don't forget there's a 1 up here. That's y to the 10th. This is tricky. If the negative is on the outside of the parentheses, it is not taken to this power. So 2 to the 6, r to the 18th, there will be a negative in front of it. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's 5. 32 times 2 is 64. Oh, why isn't it working? It must be out of ink. It's not even let me press anything. Let's try this. And what do I have here? M to the 8th. They both get taken to this power. N to the 8th. And N to the 8th over M to the 8th. If I multiply them both, they would both kind of simplify out, and we're left with just 1. Okay, a couple more. These are more complicated. On top here, I'm left with 3b to the 13th. On bottom, I'm left with 6b to the 11th. This is not the only way you can do this. You could do some simplifying first, if that makes more sense to you. 3 over 6 reduces to 1/2. 13 minus 11 is b squared on top. b squared over 2 is what I get. Here I get 12 squared over n squared. I get n to the 4th over 2 to the 4th. 2 times 2 is 4 times 2 times 16, I think. 12 squared is 144 over 16. Ugh. I don't know. I don't have my calculator with me, guys. N to the 4th, 16n squared. N to the 4th and n squared cancel, leaving me with n squared on top. I don't know what 144 over 16 is. It says I'm left with 9n squared. Okay, here I have lots of adding. Nothing to add with the a, so I have a squared. B ends up to the 13th power. C ends up to the 81 plus 3/84th power, and I have 1d left over, so that's a doozy here. Let's go over here. I have the a squared and the a to the 4th, so I have d to the 4th, a squared, all over a to the 4th. We have some subtraction here, but if I'm going to think of it as canceling, I'm going to have d to the 4th on top, and I'm left with a squared down below. Negative 5 to the 4th becomes positive 5 to the 4th, k to the 16th. That became positive because I had a negative multiplied by itself 4 times. Over 5 squared, k to the 15th. I'm happy on this one because I can just subtract. So I'm left with 5 squared k, which is 25k. And I think someone might have a question on that one tomorrow, so make sure you ask me. Here, 4 times 3 is 12. X to the 7th power when you add, y to the 15th, and we have z to the 4th. Okay, how do these work? You really need to understand your rules here, and this will be very easy. I would have 8 to the 5 plus d equals 8 to the 13. Well, for these two to be equal, their exponents must be equal. 5 plus d must equal 13. And some of you could have told me right away that d had to be 8 for this to work out. Same thing here. This will be g plus 7 equals 15. What did g have to be? 8. You could write it out like this as an equation and then set the exponents equal, or you can use your mental math skills. Here I have power to a power, so I have 3y equals 3 halves. Divide both sides by 3. Y has to equal 1 half. Here I have power to a power, and I have x has to equal 9. Okay, that's all for today. It's a lot of algebra, like I said, not, a lot of applications discussed today, but we're really going to work on those rules.